Today we learn about elements of digital communication system. A digital communication system is a process of transmitting information from one point to another using digital signals. It is widely used in applications like mobile phones, the internet, and satellite communication because of its efficiency and reliability. The system mainly consists of these elements. First one is information source, source encoder, channel encoder, digital modulator, physical channel. Here noise will be present. This is the transmitter side and this is the receiver side. In the receiver side, the first one is digital demodulator, channel decoder, source decoder, and the last one is the user. So the first block, let's discuss about the first block. First we will discuss about information source. What is an information source? It is the starting point of any communication system. It is the place where the original message is generated, and that message could be speech or a voice, like a person talking on a phone, image, a person sent via a picture sent via WhatsApp, or it can be a video, a YouTube video you upload, or any text or any data. So basically anything that carries information is the information source. What are the inputs and outputs for this information source? The input will be a physical message like sound, light, image, or any physical quantity carrying information, whereas the output is an it is an electrical signal which is of a voltage or a current that represents the original message and can be processed by electronic circuits. For example, here you can see the input for your, when you're talking on a phone, the input is your voice. It is a sound wave which is of a mechanical energy, whereas the output is electrical signal generated by the microphone. And the other names for this information source is input transducer. Why do we call it this information source as a input transducer? Before that, we should know what is a transducer. Transducer is a device that converts one form of energy into another. In communication, we usually deal with electrical signals, but the original message is not always electrical. For example, as I told before, your voice is a sound wave which is of a mechanical energy. Microphone converts this sound wave into electrical signal, but the original message is not always electrical. This is why here the microphone is an input transducer. Similarly, a camera sensor converts this light into an electrical signal, so which is also an input transducer. Now let's see the second block. What is the second block? Here we have source encoder. Wha- First we will see what is an encoder. An encoder is a digital circuit or device that converts information from one format into another, usually from analog or quantized signals into binary codes. So, this is an encoder. Now, let's see what is a source encoder. Source encoder is the block that converts a raw message signal into a digital form, like in the format of a zeros and ones. Why do we convert this normal message into a digital, in a binary sequence, in a format of zeros and ones? Because here it will remove the redundancy and makes the data as compact as possible without losing the important information. What does it means? It means the source encoder throws away extra or repeated information, so the same message can be sent using fewer bits without changing the actual meaning. Let's see some of the source encoding techniques. It will convert the text. This is a text character A into ASCII code. Now let's see what is an ASCII code. Computers cannot understand letters like A, B, C directly, right? So encoding systems like ASCII or any other Unicode assign numbers to each character. Example, for the text character A, the ASCII value is the 65, and this 65 is then stored in a binary format like this. So when you type a message, it is actually stored or transmitted as a sequence of zeros and ones. And another example is it converts the speech to a pulse code modulation. Here, our voice is an analog sound wave. Then this PCM, which is a pulse code modulation, converts this continuous wave into a digital samples, and after sampling, it does the quantization, and then it will convert this values into a sequence of zeros and once. If you say hi, then PCM breaks your voice into tiny samples and represents them as binary codes. This is how voice calls or audio files like MP3 are stored or transmitted. Let's see another example. Images. Another format is it will convert images to JPEG compression. A raw image has a millions of pixels, each storing a lot of data. Whereas the JPG reduces the file size by removing unnecessary details that the human eye won't notice, like any tiny color variations like that. You can see this example here. A raw photo of 10 MB might be compressed into 1 MB using JPG, but it still looks almost the same. You can see, right? So fewer bits are needed to transmit the image. It is one example for another example for source encoder. Now the third block is channel encoder. Third block is channel encoder. What is a channel encoder? Channel encoder prepares the data for transmission over a real channel like air, cables, or fiber. Its main job is to add extra bits called redundancy to the data so that even if noise or errors occurs during transmission, the receiver can still detect and correct them. For example, it's like wearing a helmet while riding a bike. The helmet does not change the way you ride, but it protects you in case of any accident. Similarly, this channel encoder adds protection bits so your data stays safe even if noise causes errors. Why do we need this channel encoder? Why do we need this channel encoder? Because in real life the channel is never perfect. Noise interference and distortion can change the bits during transmission. Example, 1 may flip into 0 due to noise. So let's see some common techniques of channel encoding. Here, the basic three common techniques of channel encoding is adding a parity bit. It adds one extra bit to make the total number of ones either even or odd, so errors can be detected. If the data is 1011, it will add a parity, then now it's even. Whereas the Hamming code means it adds multiple check bits in specific positions, so a single bit error can be both detected and corrected. If we give 1011 and one bit flips to 1111, if we have given 1011 and the we got is 1111, then Hamming code will detect which bit is wrong and then correct it. Here the second one is wrong, so it will correct it. Cyclic redundancy check is a it's a it will become lengthy if I explain everything. So let's just leave it here. Let's just say sends reminder to detect corruption used in Wi-Fi, Ethernet, and USB to make sure data is not corrupted. Okay. Now I told you before that source encoder means it removes redundancy, whereas now I'm telling you Channel encoder is adding redundancy. What does it mean? Why are we first removing the redundancy in the source encoder, and why are we adding the redundancy in the channel encoder? I think some of you got the doubt. Now let's see why. The source encoder job is to make the message compact by removing unnecessary repetition. If there are 6 A's here, what does the source encoder does? It compresses and just sends the output like 6A. Okay, this is like compressing your file so that it reduces the size and it removes the redundancy. It makes the message compact by removing unnecessary repetition. Whereas the channel encoder means its job is to protect the message by adding extra bits or the redundancy. These bits are not just a waste, okay? They help detect and correct errors caused by noise in the channel. Example, if I have given, as I told you before, for the Hamming code 1011 is the input, and the corrected output we got is 1111, which is the four ones, but we should get 1011. Then after doing the channel what does the channel encoder does? This channel encoding ensures we can detect and fix it. This is like adding a bubble wrap to a fragile item before shipping, so that it becomes safer. The only way to understand clearly about source encoder and the channel encoder is source encoder, what does it do? It just like compressing a file to make it smaller, whereas the channel encoder is adding error protection codes before sending it. I think it's now clear. If you understand like this, let me tell you. Okay, and now the next block is the digital modulator. What is a digital modulator? Digital modulator is the block that prepares your digital data, zeros and ones, for transmission over the physical channel. Raw zeros and ones can't travel efficiently through air, cable, or fiber. So this modulator converts this digital uh, bits into a waveforms or any signals that can move through the channel. If you give 10101, you can't directly shout that series or that sequence into air and expect it to reach somewhere, right? Instead, we encode this bit into signal variations. Like we have digital modulation techniques like ASK, amplitude shift keying, where bits are sent by changing the amplitude. Frequency shift keying, bits are sent by changing the frequency. And phase shift keying, bits are sent by changing the phase of the wave. These signals are strong enough and structured to survive the channel. What is the input for this digital modulator? Digital bits 1011 or any sequence from the channel encoder, whereas the output is a modulated waveform. And the next one is the, what is the next one after digital modulator? The next one is the physical channel. What is it? The channel is the medium through which the signal actually travels from the transmitter. This is the transmitter side to the receiver side. Without a channel, the signal would never reach the destination. A channel can be of a wide type or like a copper cables, coaxial cables, or optical fiber, or else it can also be a wireless, air, space, satellite link, etc. So what does the channel does? Channel is nothing but the path that carries your signal. You can see here is the path that carries your signal. What is the input? It's a modulated signal from the source modulator, and the output of the channel is distorted modulated signal, because a noise is added in between because the real world channels are never perfect, they add noise, interference and distortion to the signal. That is why we need error detection and correction techniques. When you're talking on a phone and suddenly hear background hiss or any static, that's noise added by the channel. Okay, now let's see what is the next one is distant demodulator. Digital demodulator. The digital demodulator is found at the receiving side of the communication system. Its job is the reverse of the modulation. It takes this noisy, distorted, modulated signal from the channel and extracts the original data back. Without the demodulation, the received signal would look like a random wave, with no meaning. So basically, the demodulator recovers the original bits, zeros and ones, from the modulated carrier signal. Why do we need this digital demodulator? Because when we transmit data, we don't send raw bits directly. Instead, we modulate them onto carrier wave. Right at the receiver, the demodulator removes the carrier and retrieves the original digital information. As I told you before, we use ASK, PSK, FSK. It's a what is it? It's a modulated. We modulated them onto a carrier wave. Now we need to convert this into original digital information, right? Now let's imagine if you send a BPSK, like a binary phase shift keying the signal. Okay, then the modulator changes the phase of the carrier to represent zeros and ones. The demodulator at the receiver looks at the phase changes and converts them back to zeros and ones. What is the input for this digital demodulator? It's a modulated signal which is corrupted by a noise in the channel. That means it's a signal from the channel, and the output of the digital demodulator is again sequence of zeros and ones. And the next one is channel decoder. Let's see what is a channel decoder. Channel decoder means it comes right after the demodulator at the receiver side. The main job is to detect and correct errors that may have happened when the signal travels through the channel. As I told you, there will be corrected data after the from output from the channel. Now the channel encoder added redundant bits for protection during transmission. Now, this channel decoder uses those extra bits we have added in the channel encoder to fix these errors. Why do we need it? Because real world channels always introduce noise, distortion, or interference. Without error correction, even a small glitch could completely change the meaning of the data. The channel decoder makes sure the data received is as close as possible to the original. What is the input to this channel decoder? It's a noisy or corrupted data bits with redundancy included. Okay. Now what is the output? It's a corrected clean data bits. If I given 1011, but due to noise the receiver got 1111, now we have hamming code, right? Because of that, the channel decoder can detect that a bit is wrong and then correct it back to 1011. So this way the receiver gets the same message that the sender gets. Now what is the next one? Source decoder. What does the source decoder does? It is the block at the receiver side that reverses the source encoding process. Its main job is to reconstruct the original message from the compressed data bits. Basically, it removes the encoding and gives back the actual information in human understandable form. Why do we need it? Because source encoder compress the data to reduce redundancy. Now the source decoder expands the compressed data back to its original form so the user can understand it. If the input for this source decoder is compressed and encoded digital bits, whereas the output is it's the original message. If ASCII, in the ASCII code example, this is if imagine this is the, not imagine, this is the binary format we got. Now if we give it this binary format to the source decoder, it will again send the the source decoder translates it back to the letter A. And also in this example, PCM, this digital samples are converted back into analog voice signal. Here we got the digital format, sorry, digital format, right? Now again this will be changed to an analog sound wave after the, this is the output of the source decoder. And the last one is the destination. You can see this is the user or a destination. What is a destination? This destination is the final block of a digital communication system. It is the end user or end device that receives the message. That means it is where the communication process actually delivers the information. Other name for it is output transducer. Just like we had an input transducer at the start to convert physical signals into electrical, here we may need an output transducer to do the reverse. It converts the electrical signal back to the physical form so that the humans can understand. What is the input for this? Electrical or digital signal. It's a decoded message. Whereas the output is human understandable message. Example for it is any TV, telephone, printer, etc. I think you clearly understood about every block. If there are any doubts in this, you can feel free to comment. Okay? Thank you.